Okay, everyone, we're going to go ahead and get started. If you're here for the Sustainable Phosphorus webinar series, you're in the right place. Our webinar today is on monitoring phosphorus in the environment. I'm Matt Schultz with the Sustainable Phosphorus Alliance, joined by Olga Borquez, our program manager. And I think we have a great webinar planned for you today, so let's get into it. The Sustainable Phosphorus Alliance, if you're not familiar with us already, we're a member organization that serves as the North America's phosphorus platform, advocating for the sustainable use, recovery, and recycling of phosphorus in the food system. We're supported by a cohort of members. Some of them have been with us for a long time. We're almost 10 years old now. And we wouldn't be able to do this without their support. So we want to thank them here on this slide. If you're interested in becoming a member of the organization, please reach out to us. We don't have memberships for individuals, only for organizations that want to join as organizations. We have a community resource through our YouTube channel where this video will be posted in the next few days. We have over 60 hours of video footage available on that channel, and it's at youtube.com/Sustainable Phosphorus Alliance. We probably have about 30 hours of just webinar material up there, and also footage from our Phosphorus Forum events and other presentations as well. One thing I'd like to invite you all to is the Phosphorus Forum, which happens yearly. This next one's happening in Raleigh, North Carolina, September 17th and 18th. It's co-organized by the Sustainable Phosphorus Alliance and the STEP Center. And we have a great agenda. You can go online and find that. The way to get to that is go to the Sustainable Phosphorus Alliance webpage, and it's right there on the splash page. You'll see a link to this site for registration. So that address is phosphorusalliance.org, or you can just search Sustainable Phosphorus Alliance in your browser and you'll come up with us. So I feel like to kick off the webinar, I feel like it's obligatory really in monitoring webinars for the host to start off by stating that you can't manage something without measuring it first. And so I'll say it here. We need to collect data on phosphorus stocks and flows in the environment if we want to more effectively target our management interventions. Today's presentations are going to focus on various dimensions of measuring phosphorus as it moves through the environment. And we're leaning heavily on USGS staff, to whom we're really indebted for making this webinar happen. We'll be hearing about remote sensing, in situ sensing, sensor networks, and the need to expand them, and what we can do when we don't have sensing in place. So I'll be introducing the speakers as they come up, starting with our first speaker, who is Michael Meyer. He's a research limnologist and ecologist at the U.S. Geological Survey. He's based in Madison, Wisconsin, and he's also an affiliated researcher at the Center for Limnology at the University of Wisconsin. So Michael, if you want to go ahead and take over, be happy to see your presentation.
Cool. Thank you so much for that intro, Matt. Hello, everyone. Thanks so much for joining the webinar today. Admittedly, I'm the first presenter and probably the least satisfying one for phosphorus-specific stuff, as I'm going to be talking more about the remote sensing aspect and all the great work that USGS is doing in the remote sensing of water quality space. And obviously, since phosphorus isn't necessarily visible from satellites, we have to rely on a lot of proxy data. So I'm going to be talking broadly about eutrophication and identifying eutrophication with satellites at USGS. Since I'm the first speaker, I know that I'm going to maybe do some big picture stuff first. We know that lakes and rivers are widely variable, and that's with respect to color and shape and spatial position within a landscape, and interconnectedness between water bodies. And so it's used, and we also know, and this is, one of those moments where I can show up some really nice remote sensing pictures. So we take any opportunity we can to show those. But not only do we know that there's a wide variety and a wide gradient of lakes and rivers, but we also know that rivers and lakes are changing in different ways, sometimes unexpected ways worldwide. Stream flow regimes are changing. Most lakes are warming. U.S. lakes might be getting clearer. The data are showing, and 77% of rivers are not free flowing, quote. And so we can use these tools, these sort of big landscape, big scale changes with remote sensing technologies to ultimately understand or discover how some of these water bodies might be changing at scales that are infeasible to sample manually. And we can use, and this is something that we can get at in different ways. So, for example, we can use the long-term time series of many of these satellite missions to look at trends over time. We can look at phenomenological drivers or phenology. We can look at in situ gradients using these sort of natural gradients across different latitudinal gradients to create these sort of observational experiences. And if we get really lucky, sometimes we can think about processes and patterns occurring with these data. And I think a great example of this that's being developed across several agencies for remote sensing data is the Cyanobacterial Assessment Network, or the Cyan tool. And if you're less familiar with the Cyan tool, I have this screenshot where basically what it is it's kind of this GUI interface system, and I'm happy to drop a link in after I've finished presenting, where any user can click on an individual water body that's likely within the NHD. And you can and what the Cyan tool does is that it reconstructs estimated cyanobacterial abundance as sort of that proxy of eutrophication, and it identifies those cell counts within different ranges, so low, medium, high, very high. And this is for Lake Mendota, which I can see outside of my office window. And what we can see here is that, for this time span between August through November 2024, Cyan was able to pretty well capture these dynamics from going from high cyanobacterial abundance to medium to low. That kind of follows that end of year cyano presence that we might expect in a given lake. So that's an example of a currently developed and kind of borderline operational tool that's led by the EPA, but also with great support from the USGS. And I'm happy to talk about what we do to help that tool remain functional. But also on sort of that research and development side of things that are happening, I'm really excited to be the project manager and a co-collaborator on AquaSat, which we're now calling AquaMatch. And basically what this is it's a harmonized tool of water quality data and remote sensing reflectances to empower end users to build their own remotely sensed water quality model based on their own in situ knowledge or the specific scales that they're looking to get at. Now, version 1 of the data set was already published in 2019, led by Matt Ross at Colorado State University. But currently, we're in this something called AquaSat V2. I affectionately refer to it as AquaSat CR for continuing resolution. But basically, to get an idea of what's happening with AquaSat or AquaMatch now, is that version 1 had pretty limited variables. It included chlorophyll, total suspended sediment, Secedis depth, and chromophoric dissolved organic matter. And it had this sample inclusive philosophy, where we would pull data from the water quality portal across all these agencies and just include all data, all samples, and treat them all as equal. What AquaSat version 2 is doing is we're expanding that variable list and we're instituting this sample tiering philosophy, where I'm going to walk through an example like with chlorophyll, where you can imagine what are your highest quality chlorophyll samples? They're probably from an HPLC. We probably know the depth that's associated with those samples. We know if it's above or below the method detection limits, stuff like that. So what AquaSat V2 is doing is ultimately making those metadata more consistent and more tabular or more tidy in this tabular format, so that it allows an end user to not only know what goes into that sample estimate, but also filter to a given tier level. We're also producing extensive metadata documentation and creating this data set with a user-focused design. And also, lastly, we're instituting an automated workflow management software that will allow for continual updating of the data set as new data become available. So I feel like that was kind of like drinking from the fire hose of what's the difference between these two examples. So I'm going to walk through an example of one of these user manuals that we've created with Aquasat, just to get you a sense of what's the sort of documentation. Now, this example is for chlorophyll. However, phosphorus and nitrogen are two water quality constituents that we are chomping at the bit to get at. So I would anticipate those data coming live in the next 6 to 12 months or so. So I'm gonna reshare a Zoom screen. So let's hope this goes okay. Yeah, this. Okay. So hopefully that's coming through okay, but basically what you can imagine is that for every aquamatch variable, and right now we've published chlorophyll, Secedis depth, and dissolved organic carbon. I would expect total suspended sediments to come out in the next 2-ish weeks. But with each of those variables has this compendium, this book down compendium that walks through exactly how we tiered the data, how we download the data from the water quality portal. So here you can see all the samples that are coming within the contiguous United States, Alaska, Hawaii, American Samoa, Guam, and Puerto Rico. How we tier the data, so like how we handle NAs, how we handle all the methods. For chlorophyll alone, that was 498 unique methods that we compressed down to about 5. How we handle comments from the field, how we extract depth from anything from the actual depth column as well as all the comments. How we handle time codes for things like daylight savings time. How we anonymize the data in case the sample collection had someone's email or phone number in it. And then we also walk through how each of these decisions influence the number of samples in the final data set. So we started with 4.7 million samples. And then we notice that as we go through each of these filtering steps, we slowly but surely lose some samples. Some of them have fail detected language. So we remove samples where the lab might have included fails. We remove samples based off of the MDLs, if it was an approximation versus a real value. If it's the units made sense, if there was depth data associated with it, if it fit one of these methods tiers, if it had any sort of flags, there's a miscellaneous field, if it was an unrealistic value, and then also simultaneous records. And so what we're able to do is to start with 4.7 million chlorophyll samples and get down to 3.4 million simultaneous samples, where each of those samples are tiered based off of this restrictive, so what we would consider those highest quality data, the narrowed, which would be maybe something like if it was collected with depth, but it was from a spectrophotometer or a fluorometer, and then the inclusive tier, where we're not 100% sure on all of those variables, but we're pretty sure that it's a realistic value. And like I said, this is just for chlorophyll right now, but we are definitely working through, or I really hope for nitrogen and phosphorus to come out, like I said, within the next 6 to 12 months. So keep an eye on that. Now let's go back to the slides. Okay. Another example that I'd like to show, it's a little bit of a sidesteppy thing, but we also have the national scale remotely sensed lake trophic state data set, which uses the Landsat satellites to look at changes in annual trophic state classifications for about 55,000 lakes throughout the contiguous United States. Now, if you're less familiar with this idea of trophic state, basically you can think of there's three main types that the data set can differentiate. We have oligotrophic lakes. So this is Flathead Lake. It's large, it's deep, it's blue. It's the type of lake that you want to swim in. And then there's Lake Mendota, one particularly green day. It's green. There's lots of algae in it. It's the type of lake you want to fish in. The data set also does include dystrophic lakes, or these browning, very humic lakes. But given this conversation, I want to focus on these three. And basically what it does is it uses the US EPA's National Lakes Assessment in tandem with the Landsat mission to predict a lake trophic state in a given year based off of the surface reflectances, even where those models are built off of in situ concentrations. So you can think of this as kind of like an application of what one might be able to do with the AquaMatch data set. And we can see things like, where are those blue lakes, those blue oligotrophic lakes? And generally this data set is already showing that oligotrophic lakes are kind of where we would think they would be. They follow mountain ranges. They're in the Pacific Northwest. They're in the upper Midwest and the Northeast. Whereas oligotrophic lakes tend to be in the plains, in high ag areas, and notably not where we're seeing those oligotrophic lakes. And just because I really enjoy this map, if you're curious where those dystrophic lakes might be, or those brown lakes, dystrophic lakes tend to be in the upper Midwest, so in northern Wisconsin, northeast Minnesota, as well as in that upper or the northeast as well. So that's at the national scale. What we know that some folks are doing at the local scale is, using the time series in these data sets to ultimately identify eutrophication of systems where we really only have recent observations. So for example, this is for a reservoir in Idaho. It's either Idaho or Montana, Island Park Reservoir, where we only some local crews started sampling recently, and they always thought of that system as a eutrophic environment. But what we can see using the Lake Trophic State US data set is that we can create this retrospective analysis where actually, in the late 80s and 90s, the reservoir was mostly oligotrophic, but then seemed to go through this sort of state change starting in 2000. And indeed, we also know that a lot of local end users, particularly in the Pacific Northwest, are really interested in understanding these landscape-wide arrangements of lake trophic states. Where here in this Montana, Idaho area, you can really see where those plain regions start popping up relative to those more mountainous regions, where you see eutrophic lakes in the plains, oligotrophic lakes in the more mountainous areas. Okay, and I can drop links to these in the chat, but if you're interested in accessing the data and as well as the paper, it's all available on the Environmental Data Initiative. And with that, I'll pass it off to the next presenter.
Great, thanks so much, Michael, for that presentation. I'm going to go ahead and share my screen here for the Q&A. And Olga, if there are new questions that come in, please feel free to put them in there. One question that came up is whether your data sets cover just the US or if they're global.
Yeah, so for AquaMatch, or actually for all the data sets that I've presented, they are for the United States.
Okay, great. Mm-hmm. And question I had was, do you collaborate much with, say, Fish and Wildlife Service about how these trophic states are impacting the ecology?
Not currently.
Okay. You're open to
opportunity abounds.
Yeah, okay, great. Olga, were there any other questions that came in, or is that it?
Nope, that was the only question.
Okay, great. If there aren't any more questions, we'll go ahead and move on to our next speaker, who is Colin Peake. Colin is a physical scientist for the US Geological Survey, Central Midwest Water Center, Science Center in Urbana, Illinois. He currently works as a physical scientist on nutrient super gauges, and he's going to be talking to us about gauging and other things today. So, Colin, if you want to take over.
Excellent. All right. So, like Matt said, my name is Colin Peake. I'm a physical scientist with the USGS. I work out of Urbana, Illinois, and I've been with the USGS for about 10 years, mainly doing nutrient science. I was pretty excited to give this presentation today. A group of people who actually love phosphorus science and want me to talk about it was pretty exciting to me. I will definitely jump at a chance to do that. I'm mainly known for my phosphorus work, but I've also done a lot of nitrate and chlorophyll science. And I've helped numerous federal, state, local entities set up sensor networks, kind of the how, what, when, where, why, all the questions that arise because budgets are tight and sensors are expensive. That's kind of where I come in. So I don't think I need to tell you why phosphorus is important, but why are people asking me to collect phosphorus data? I've helped stand up a lot of science networks around the country in a ton of different environments, but I'm going to just stick with my experiences here in Illinois. So surface water loadings, essentially how much phosphorus is going past this point in a river. If you want to reduce phosphorus in a river, you need data to tell you how much phosphorus is at that point in the river. Algae blooms, phosphorus is a limiting nutrient in a lot of environments. So how does changing the amount of phosphorus potentially help or change the algae blooms? Best management practices, again, if I go through the effort of cover crops, buffer strips, whatever your BMP is, does it actually accomplish what I want it to? And finally, regulatory compliance, highly variable state to state on that one, but sometimes this is the result of some litigation. We've been asked to measure various water quality parameters. So why is it so difficult to measure phosphorus? And the simple reason is I can't shine a light into a raw river water sample and figure out how much phosphorus is in it like I can for something like nitrate. I have to chemically manipulate the water sample. And really, phosphorus actually isn't that hard to measure. The methods that we use in the laboratories were developed in the 60s, and we've been measuring phosphorus the same way largely for decades, but now we want to automate that method, which is where it gets really tricky. So when you start trying to automate phosphorus measurements, it gets really complicated fast. There's a ton of engineering required. In the USGS, for my needs, what I want is an analyzer to run for 6 weeks, without me having to be there or touch it. And that's a key point on scaling up continuous phosphorus measuring. It can't be more labor intensive than me sending out a tech to collect a water sample. So how do we do that? I don't have time to get real deep into this, but there's just a lot of considerations. Your method and parameter type, how your fluidics and filtration are going to function and not clog. The list is long. And I'll give an example kind of how this can spiral out of control. Typically, an analyzer uses one of two methods to determine phosphorus, and these are commonly referred to as the blue or yellow methods, and that's after the color change that occurs, which is dependent on the amount of phosphorus in the sample. And the speed of that color change is dependent on temperature and determines how fast the analyzer can function and collect new data points. So here in Illinois, my river could be anywhere from freezing in the winter to 80 degrees in the summer. So that same reaction might take a minute or two in the summer, but it might take nearly an hour or something in the winter time. So this changes my data collection rate and a host of other things. So if we solve that problem by heating our reaction chamber so it's always the same temperature, now my reaction takes the same amount of time at every sample, but then heaters are energy expensive. Now I need a lot of power next to a river that floods, right? So that's not an ideal scenario. So here's a couple of videos of common conditions that we have to deal with. Most of these analyzers are not meant to go where I put them. Putting water quality equipment in a river and having it not get destroyed while collecting data representative of the river at that point is actually really hard. Manufacturers are always amazed at where I'm putting their equipment, not because it's these big cabinet style analyzers that are built for water treatment facilities, which have a lot more controlled environments. So I have to do my own engineering to make these things work most of the time. So what does that look like? A lot of times we run the equipment on elevated platforms with AC power and pumping systems, where I bring the river water to the analyzer. They consist of the phosphorus analyzer, a tank that holds the analyzer filter, a pump to bring the water to that tank, and then all the electronics to tell the analyzer what to do and run the telemetry so we can see it in real time on the web. These setups allow for stable, safe working environment for the analyzer under all river conditions like the floods and the trees and ice that you just saw. So back in 2020, I started testing analyzers in a climate controlled shed. I chose 4 very different analyzers, of which the hydrocycle is now defunct and the Easy 7800 underwent a complete overhaul. But that's okay. Technology moves super fast, but the lessons on why they failed are still very much relevant. There's a link to the paper down there if you want to read all the details, and I can put that in the chat after the presentation here. So I put 4 analyzers to the test over the course of a year to see what they could do. I really wanted to kind of get them dirty, run them hard, see how many maintenance problems popped up. The analyzer you get initially from the brochure works great. It's only when you run them for a long period of time, things start to break, you really see how they're really going to perform. So here's a nice time series of all 4, and you can see they mostly trend together, but the table on the left-hand side kind of tells the real story there. So the key factor that determined data quality and data coverage was their ability to handle sediment in the water. Rivers have a lot of particulate, typically, here in the Midwest, and you have to either block that from entering your analyzer with a filter or keep it, from clogging your fluidics, and usually you have to do both. So filters and fluidics play a delicate balancing act, because the more samples you pull through a filter, the larger it needs to be. And then there's microfluidics that try and solve this problem by pulling in tiny amounts of water, allowing for a much smaller filter. The problem with microfluidics is you tend to have, much smaller room for error because your volume is so small. So failure is acceptable. What do I mean by that? Let's go back to some of these key elements again. So what combination of these elements is going to work best? Does it require a small adjustment or a complete rebuild? My philosophy is let's keep going and build off of the failure and make a better analyzer. That's really what we're after here, is how can we get better, cheaper data? These kinds of R&D experiments are really all about your return on investment. People want this data, so let's find the correct tools to get it. Once you know what analyzers work best and where, that reduces risk. I can't rely on a salesman to tell me what it should do. At this point, I tell the salesman kind of what it does. And the reason is few people can afford to pay $20,000 to $80,000 for something that underperforms and can't meet scientific goals. No one wants to be the guinea pig in that sort of situation. So someone has to take the first step and take that initial risk. In this case, it was me slowly building up the knowledge over the course of a decade with USGS programs. But this way I can go to a cooperator with confidence and say, I know this is expensive, but you'll get this great new data set and a fresh perspective, and I know I can deliver on their scientific goals. People pay for innovation, right? So what can you do better than anybody else? What sets you apart? What justifies the cost? So the key point here is what balance of all these parameters allows for an affordable analyzer that works under a wide range of conditions with low maintenance. It's the only way we're going to be able to scale up our real-time phosphorus data collection, is if we find a balance of all these engineering considerations. All right, so switching gears a bit, what am I currently working on? I have 2 analyzers that are in testing right now, the Green Eyes New Lab and the Clearwater Phosphate Sensor. The new lab is a bit different in that it's targeting total phosphorus and orthophosphate at the same time. To do total phosphorus, there's a couple of extra steps. You need a digestion, and you need to break apart anything that might be holding onto its phosphorus, basically. So this requires extra reagents and extreme heat and pressure. But the bigger issue is total phosphorus requires raw, unfiltered river water, and I just got finished telling you how hard it is to do that, basically. However, if you can do it, it's a extremely valuable data set that a lot of people are after. So a quick example of what that looks like in the data. The red is orthophosphate, the dissolved portion, and the blue is the total phosphorus, and you can see how much of a difference there is in this system. Sometimes the dissolved portion is only a part of the story, which is what makes the total phosphorus so appealing and valuable. But like I said, sediment is an issue, and it's really hard to deal with. So here you can see some of the sediment that builds up on the syringe head, and it binds that syringe and causes it to leak. We think we fixed this issue now, but that just speaks to the constant kind of evolving nature of this technology and the need to test and kind of work out the kinks. All right, so the first impressions of this analyzer are that it's very customizable to your environment needs, but it has a high labor, making scale up costly. It has taken me a while to get it dialed in, which is a problem, but it has that potential, and it's trying to get at a really unique, first of its kind data set with total phosphorus, which can be extremely valuable. And then the other analyzer that we're working on right now is the clear water phosphate sensor, which is a microfluidic DC powered, so it can run off of a battery, and it's all self-contained. It's meant to be used more like a traditional water quality sensor that you can manually put in the river, and it performs its analysis underwater instead of the big cabinet styles, which have to be kind of out of the river, out of the flood zone, and all that kind of thing, and require a lot more power. And you can see with the microfluidics, you can have these tiny filters, and that green filter on the right there is only the size of a dime. So it remains to be seen how well that performs over some sediment conditions right now. Here's some of the initial results shown here. I only recently got this one deployed, so I've only had it running for about a month, but so far it's tracked well with the phosphates there in the gray and the clear waters in the blue. And I have a couple of lab samples there, which are the black triangles, but we're waiting on a lot of our lab samples to come back yet. So we'll see how it stacks up once we get some more data. So first impressions on the clear water are that it's portable, allowing for less infrastructure, low maintenance, which is good, and that you don't have to do much to it, but that's also kind of on the flip side bad, in that if it breaks, there's not much you can do to fix it without just sending it back to the manufacturer. Recording the data can be a bit challenging, and they need some programming knowledge, and because it doesn't control for temperature, that sometimes cuts down on the number of samples you can do when it's cold. And it takes a lot of work to do these projects and collect all the verification samples using the data analysis. So special thanks to the people that helped me gather and process those samples. Here's my email if you want to send me some follow-up questions also later on. And with that, I think we can open it up to a couple of questions if there's any.
Great, thanks, Colin, for that presentation. There was just one question, might need a little clarification, but it was, do you precipitate phosphorus in the form of calcium phosphate for analysis? And if yes, can you tell us the name of the precipitated calcium phosphate? I assume that means the species, the chemical species.
It's all converted to orthophosphate for analysis. So that's what the chemistry is behind it.
Okay, great. So yeah. And then, so orthophosphate, okay. And the counter ion doesn't matter, is what you're saying.
I don't think so, no.
Okay. Okay, great. One question I had was, you're measuring the phosphorus concentration in the water column, right? Are you doing sediment measures as well?
Yes, yeah, and it depends on the environment. So typically your rural ag tends to be more sediment based in your phosphorus concentrations, and then your urban environments tend to be more dissolved. So yes, we do a lot of total suspended sediment analyses as well with these analyzers, so that you can kind of get at both portions of the total and the dissolved at the same time. And then in Illinois, we obviously have Chicago, so like a lot of that's in the dissolved form. So it really depends on what your environment is you're trying to measure.
Okay, great. I think that's it for the questions. We're going to now go on to our next presentation, which is coming from Christopher Oates. Chris is pursuing a PhD in biological and agricultural engineering at North Carolina State University, and his work is focused on tracking the environmental and social impacts of nutrients on watersheds as they move downstream. So, Chris, are you able to take over?
Yep. Yes. So, like Matt said, I'm a PhD student at NC State, studying biological and ag engineering. This work just came out recently in November, and it's kind of a collaboration from a lot of people at the STEP Center. And it's looking at surface water nutrient monitoring, specifically in agricultural regions, and what can we do to expand monitoring efforts. So a little bit of background, despite a lot of public concern and a lot of people, definitely caring a great deal about their water quality, over 40% of the U.S. streams and rivers and other, freshwater bodies are impaired due to elevated nutrient levels. And some of that is caused by a couple gaps in the Clean Water Act. And while the Clean Water Act has significantly reduced pollutants from point sources, it's largely exempts non-point source pollution. And a lot of that non-point source pollution is from agricultural lands. So it's currently unknown how well nutrient water quality monitoring efforts capture some of these nutrient inputs from watersheds that are agricultural. And this is kind of the main motivation for this work. So our goals, we had 3 of them, and they were to evaluate challenges that stem from the Clean Water Act's limited ability to address agricultural non-point source nutrient pollution, and also to assess the current state of nutrient monitoring in the contiguous U.S. And also we wanted to propose some improvements to nutrient monitoring networks in the U.S. And we're going to talk about the latter two. So for this work, we used nutrient inventory data from the EPA, and this database was made in, I believe it's 2012 was the most recent version of this data. But it uses nitrogen and phosphorus input data, and those, and it's on the watershed scale, the Huck-8 scale. And it basically models the nutrient inputs from fertilizer cells, and also looking at livestock counts, and that basically is a proxy for manure. And these inventories are available in these 2 different papers. There's a Sabo et al. 2019 and a Sabo et al. 2021. And this picture kind of shows how that database looks when you put it on a geospatial scale. We see like a lot of, production, or a lot of nutrient inputs in, the Midwest and the South and the parts of the Southwest as well. So for this work, we wanted to look at active nutrient monitoring stations in the U.S., in the contiguous U.S., and we decided to include stations that had taken at least 40 samples and also had recorded at least 40 observations and collected at least 40 samples from those observations between January 1st, 2012 and December 31st, 2021. And this approximates to about 4 samples per year, so about seasonal. And there definitely has been studies to show that, monthly sampling or bi-monthly sampling is a lot better to characterize nutrient fluxes. But for the sake of this paper, and also where we could have data to analyze, we decided to use a seasonal data collection as our limit for what counts as active. So using those criteria we just mentioned, we use stations from the Water Quality Portal. And these mainly come from the EPA's storage database and USGS's National Water Information System database. And in total, there were a little over 16,000 stations that met the criteria of activity. But some of these stations were not located in watersheds that had nutrient inventory data. And on this map, you can see there are some watersheds that are just shaded white. Those are places that don't have nutrient data from the SABO inventory database. So all the water or all the water quality monitoring stations that were located in those watersheds are shaded in yellow. We just wanted to show them on the map just to show where monitoring happens, but for the sake of this analysis and this study, all the yellow stations were excluded from any further analysis. So we wanted to compare nutrient inputs. We had nutrient input data, and we also have station locations. So we wanted to basically assess monitoring density and looking at, how overloaded or loaded certain watersheds are to track their nutrients. How much how much input are these stations tasked with monitoring? So we took that livestock manure and fertilizer database from 2012 and combined it with the monitoring station data that I just mentioned. And we classified our watersheds into 9 different categories, and those were based on how their nutrient input and also the station density. So these maps, they're a little confusing at first, but once they're explained, I think they're pretty cool. So we have a phosphorus fertilizer application and a manure production map, and these also exist for nitrogen as well. But we're just going to talk about phosphorus to make it a little easier. And then on the right-hand side, we see the legend. So as you move to the right on the legend, those are areas that have an increased amount of phosphorus input. And then as you move up on the color bar, those are also stations that have, or watersheds that have a higher amount of stations per watershed. So we thought that the category or the categories that were most interesting to us were the sections that are labeled or circled in red. And these represent watersheds that are very high on the nutrient input and then varying levels of station density. So nationwide, monitoring is a combination of many different federal and state and also local and municipality programs, and it creates a rather extensive network, but we found that it's kind of incomplete. What we found is that over 1/3 of watersheds have 0 nutrient monitoring stations. And then we also found that over 80% of watersheds have 10 or fewer stations, which in some areas, especially more agricultural regions, that could be a potential area for concern. So getting into some of the monitoring station and comparing some densities that we found, many agricultural regions are significantly under monitored relative to their nutrient contributions. And we see that in regions like the Midwest, some of the parts of California, and also parts of the Gulf. We see that these are areas that do have pretty increased nutrient input. This map is for fertilizer, phosphorus fertilizer, but again, these maps do exist for fertilizer for nitrogen and phosphorus, and also manure for phosphorus and nitrogen as well. And we see that these areas are some of the areas that are shaded in brown are the areas that we found to be the highest in the nutrient inventory or the nutrient input category, but have no monitoring, right? So that 7% I mentioned earlier are these brown areas. And even parts of the Midwest that are slightly more monitored are still very, very high in nutrients. So we thought these would be areas that would be at least interesting and could provide potential case studies for how to improve monitoring in certain regions. But on the flip side, we also found areas that do a pretty good job of monitoring very high nutrient input areas. We see here, parts of the Lake Erie Basin and parts of eastern North Carolina, the Delmarva Peninsula are areas that have pretty high nutrient input, but also the monitoring coverage is rather dense. So although there are a good bit of inputs from agriculture and other practices, the states and federal programs in these areas do a rather good job of monitoring. And also a lot of these places do have different maximum loads and things like that for their watersheds. So we didn't test the correlation between where watershed protection programs and things like that exist, but if you look at this map, these are areas that are pretty highly regulated. So we do think there is some correlation there. And then, I mentioned that these areas highly monitored, densely or highly monitored watersheds that are very high input areas could be related to having regulatory mandates like having total maximum daily loads, but also places that have frequent algal blooms. Maybe citizens and people in the community advocate more for those areas we monitored. So increased visibility and local advocacy, maybe places that are really important to tourism. All those kind of are factors that could play into areas becoming more heavily monitored. So we've talked about under monitoring, and other speakers have also talked about the importance of monitoring, but why is this important, right? Well, limited monitoring reduces our ability to accurately assess nutrient loads and concentrations of impaired waters. And this is particularly important since we found that 7% of watersheds are in this high nutrient input category, but in the unmonitored category. So that's areas that are, we don't know that much about the nutrient loading in these areas, but we do know that we don't know much about the water quality of these areas, but we do know that nutrient loading is high. And this is also really important because a lot of models like SWAT and Sparrow can estimate nutrient loads in these areas that are, high nutrient input in lieu of monitoring, but these estimates can be highly uncertain. And models cannot fully replace observational data that we get from monitoring. And other work that myself and lab and other of our colleagues are working on, we found that expanded monitoring can also help address socioeconomic issues related to water quality monitoring coverage as well. So there are a lot of benefits to increased monitoring. And as we kind of heard too, enhanced monitoring enables more cost-effective nutrient pollution management. If we know areas that are, that could potentially be problem areas in the future, it's a lot easier to create strategies that are going to be, help try and, alleviate some of these issues before maybe they happen. But also we could use advanced technologies to overcome some logistical barriers because a lot of these areas are more rural and less accessible areas that are, more agricultural and things like that. So it would be, more difficult for technicians and people to sample often there, right? So, things like remote sensing, as we heard earlier, could be, it's just one of the many different technologies we could use to help sort of overcome some of these logistical barriers and data collection. And if this was something that was, interesting or anything I said sparked your interest, I haven't looked at the chat yet for questions if there are any, but if you scan this code, it'll take you to a link where you can read this. This just came out. And yeah, I appreciate y'all and I appreciate the invite for being able to speak about this stuff. So thank you.
Thanks, Chris. That's really great work that you've done, and I know you've gotten a lot of kudos at the university for the work that you've been doing too. So appreciate your joining us. We didn't have questions come up other than someone requested that that if you could put a link to the SABO papers that you mentioned, the 2019 and 2021 papers, and share that with the group, that would be welcomed. If you get a chance to do that.
That sounds
A
great. Yeah,
question just came in, actually.
Oh, question just came in. Hot off the presses. Okay. You want to go ahead and put it?
Oh, okay. I see it. I just read it. Yeah, that's a great question. For the
Olga, you want to put that in the Q&A? Thanks.
Yeah.
Oh yeah. So someone asked, were there differences between nitrogen and phosphorus in terms of monitoring gaps? Since the EPA and USGS use a few different codes for how they assess they use different codes to actually say, okay, these are sampling, we're sampling for this, sampling for that, different analytes and whatnot. We decided to use the catch-all term as nutrients when we decided to pick these stations. So these are stations that monitor for nutrients more broadly. So we didn't actually assess for stations that are looking at phosphorus, stations looking at nitrogen. We just looked at stations that are recording samples, and those samples that they recorded are deemed as nutrients. But yeah, that's a great question, and it would be really cool to look at in the future.
Great, thanks. If I were to guess, I'd say phosphorus is less monitored, but we'll see. We'll see what your research tells us. Thanks again, Chris.
Okay, no problem. Thank you.
Yeah, great. We're going to go on to our last two presenters, last but not least. So we have Noah Schmadel, who's a hydrologist with USGS Water Resource Mission Area. And among his many research interests, he studies the sustainable management of water resources, including both water quality and quantity. And he's joined by his colleague, Olivia Miller, who is a member of the Utah Water Science Center. And her current research focuses on spatial and temporal analysis of groundwater and surface water quality, and on the relationship between land use, climate, and hydrology throughout the southwestern United States. So Noah, I think you're the one who's sharing slides, so I'll just let you take over here.
Yeah, so thanks, Matt, and sorry for the confusion. Today I'll be presenting the slides, and so like last week, Olivia gave a talk, and I felt like it was my turn, and so today you're stuck with me, but this is very much shared work. Olivia and I have been working on this project for the past few years, and we're joined by a really great team that's just quite a depth of skill and knowledge, and we've learned a lot from them, and we've gained a lot in terms of progress and our own skill development. And the title we have today is quite vague. We did that kind of intentionally, and this is to point out that USGS has been working on this problem for a number of decades. And so today, Olivia and I are fortunate to share some updates of where we are. And so this idea of extrapolating monitor information, and that's a lot of what Colin was showing, the on the ground work in the field, and what Christopher was showing is really leading to this place of taking that information that's observed and putting it to places we don't necessarily have that information. So it's like connecting the dots. And something that Christopher pointed out is models can't replace observation, which is a great, powerful, important statement to make. But we really need models to get to the point of interpretation, and that's where we think the information for decision making is really important. So, in terms of the project that we're presenting today, is we think we really need a comprehensive look of how water quality changes over space and time to really assess how much water is suitable for use. And of course, we have to consider ecosystem use. That's an important part of all of this. And so today we're presenting on total nitrogen and total phosphorus. But any of these methods can be applied to other constituents, like sediment. It was brought up during this webinar. Salinity is another important constituent to consider, and there's other work being done in those areas. And also, these frameworks can be used to quantify water quantity, like stream flow, and so it's all related. But we're really after making progress on the nutrient side, and one of the main pieces we're really excited about is introducing dynamics into these type of large scale models, where we can look at how things change over time, and in particular we focused on the period from 2000 to 2020, and it's really a matter of data limitations, but the idea is we set the framework now, and we have the ability to extend that in time to more of a real time status in terms of condition information. I mentioned the interpretation, so that's where the development of these models is really important, and also we want to develop frameworks that are transferable. And a question came up earlier on in the webinar, like, is everything we're doing based on US data, or is it global application? And in our case, we're using US data, mostly USGS, but the idea is this can be transferred to any watershed, any basin globally. Okay, and so where we have turned is the Sparrow model, the Sparrow framework, and that's something that Christopher mentioned in his talk previously. And really, the reason we start here is, this has a lot of advantage. And starting with just the monitored loads, that's really the idea, is we try and extend that knowledge, or what we observe at point locations in real time, to everywhere in space. So every river reach, every reservoir, every lake, we have some indication of water quality information, but we also have to pay attention to uncertainty in extending that information. And I think Christopher was the one that really made a good point of that. And here I just highlight some of the key features. And so I bring this up to mention that it's very flexible. We can improve any aspect, any areas of these, like Michael mentioned, remote sensing, lakes and reservoirs, and those are things that we can directly and explicitly bring into these models to make things better, more accurate in space and in time. And so we're really guided by this comprehensive perspective, where we want to track things from headwaters to estuaries. We want to look at how things accumulate through a river network. We use simple physics to guide us. And I I say that point that this is an active area of research, and we're very much interested in improving this. And this is something that Michael's remote sensing work could really very much help. That's just a quick idea there. And so we'll look at this Y variable. This is the dependent variable in our model. So this is what we're trying to predict to. And someone asked, what's the coverage of phosphorus versus nitrogen? And the phosphorus are the green dots, the nitrogen are the magenta or pink dots. And quick note here, Christopher was showing, these are the same data. They come USGS data, EPA, water quality portal. So we're pulling a lot of the same water quality data. And he noted something like 15,000 sites. But for these models, we've had to really filter down, and we've gotten it down to about 2,500 or so sites. Little more phosphorus than nitrogen. And the reason is we need a good number of discrete samples. We need a good coverage. It needs to cover a certain number of years. Like, we can't use discrete data that was collected for 1 year and say, yeah, we know what the water quality is for 20 years. So we need some good coverage, and it needs to be paired with continuous stream flow to really be of use in the model. So that's what really dropped that number from 15,000 to 2,500, which is a little discouraging, but there's still really good coverage. And we could set up a whole nother webinar for coverage of data, and I'm really happy to see that Christopher is making some headway on those topics. So the idea is to connect all these dots and to make predictions across all of space. And the example that this was shown earlier in the webinar, this is really the current state of knowledge, a long-term understanding. So we need to look at the gradients across large space to make inference in terms of what's the spatial distribution of water quality. In 2012, the year noted, but that was just kind of the mean year that everything was averaged over. And so this is a really good picture of really the total phosphorus loading and concentration across the country. But where we're going with this, and what we really have identified as an important next step, is bringing in dynamics. And we've selected seasonal dynamics. And you can kind of see where the increase in information comes. The red line is that 20-year average, that 2012 mean centered year. That's kind of the total nitrogen load estimated from that model. And when we're bringing in seasonal dynamics, that's the black line. So that's our new model prediction. We compare it to observation. That's the colored line. There's a lot going on here, so please bear with me. And we have 84 seasons that we're observing and trying to predict to. And it's colored by stream flow, just to give a sense of, well, does total nitrogen go up with stream flow, or does it get diluted? And so in terms of total nitrogen, total phosphorus, the general pattern is there's an increase in loading or flux with stream flow. It's not necessarily being diluted. So on average, we can kind of make that assumption. And something Christopher mentioned was, uncertainty in these models. And a really important part of all of this is we want to say, if we're predicting in a place we don't have one of these monitored real-time locations, that we can assess the uncertainty and how accurate we are at predicting. So when we look at this time series and prediction relative to our observation with the confidence intervals, we think it looks really good. And then, so now that we have a model, we're taking this and saying, well, can we identify the primary sources of nutrients? What are the drivers of those? And now that we're no longer assuming equilibrium conditions for long-term estimation, we can look at the role of stored contaminants. We can start to look more at their contribution to the overall mass balance. And just to get a sense of how this model is built, we take that Y variable, all those observations, and we make predictions. And so on the left is our predicted model relative to the observations, and looks good to us. We don't see any real big outliers, any strings of data. We've worked really hard to get things as representative possible, but you can also see there's scatter, there's uncertainty. And that's something just really important to acknowledge, that when we extend observations to unmonitored locations, there are uncertainty we have to track and take into account. And on the right, this is the list of variables. These are the data we bring in the model. So we're trying to track individual source components. And it was brought up previously, like fertilizer and manure are big components. And so the model, what we're trying to do is we're trying to do a comprehensive accounting. So any dominant source that's delivering mass to a stream, we're trying to isolate and track these individual pathways. So like number 4, atmospheric deposition, that's for the nitrogen model only. We're not necessarily assuming that that's a dominant pathway for phosphorus, but things like urban, open land cover, yeah, it's probably contributing nitrogen and phosphorus. And so when we run this model, we can start to pick apart and say, what are the rates? What's the seasonal rate of fertilizer and manure that gets delivered? What is the mass generated per area? So if we have cover data sets, and then also things like septic systems, what's the mass per household? And then all of this is related to the storage lag component. So now that we are running a model that is dynamic and not in equilibrium, we have to lag mass through, and we're quantifying that that's quite a big component. So just to give a sense of some of these data sets, there's wastewater treatment. That's a big component. So that's a point source that's almost fed directly into the model. But then one of the other source components I mentioned, atmospheric deposition, these are big challenges. When we go to say we want to make predictions across all of space, we also need the data sets to be as representative across space as possible. So this goes back to Michael's talk, where we have remotely sensed data, but we need some consistency of it before we can kind of represent it and quantify it within the model. And so those were all the source terms. And so we also are tracking things like the hydrology, soils, other infrastructure, in how that interacts with the sources. And we see things just very quickly like precipitation. We see a positive correlation with all the source terms, or a positive interaction with the source terms, meaning increased precipitation. We can probably assume that we'd see more nitrogen and phosphorus getting delivered to streams. And then that changes spatially based on soil makeup and composition, and if there's other infrastructure like tile drainage within agricultural regions. And a big factor of the Spiral framework is an ability to track things through the rivers, lakes, reservoirs themselves. And so we bring in data for the aquatic component. And so we're really excited to eventually, hopefully use some of Michael's data sets and have a better representation of what the role of lakes and reservoirs are in terms of removal and storage in nitrogen. So I mentioned the equilibrium static representation across space. We're now at a point where we have the data sets to predict at a seasonal time step for at least 20 years, 21 years. We're building data sets to keep that more in real time. So that's the plan. The next step is to keep this going. And we're just at a point where we're writing this up, and we'll give a little bit of some examples of like what we can do with these data. Since it's across all of space, it's 84 periods, 21 years, 84 seasons. And we've just started to do some comparisons. Like if we look at the source composition, West, Midwest versus East, there's some things that jump out. It's interesting to see the influence of fertilizer in the Midwest versus the West. And a storage component, the bluish color, the models are indicating that there's a substantial lagged component, that when you put fertilizer down, it takes time for it to eventually reach the stream. Not all of that mass is delivered within that same season. And the purple color, wastewater treatment, treated wastewater. And so we're trying to track these kind of major components. This is just an example. And so phosphorus, the source composition is a little different, but we still have this lagged component. treated wastewater is still a big component. So let's just give an example of where we're going with this. So now that we have a kind of better understanding of loading, stream flow across many different seasons, across 21 years, we can start to update our understanding of concentration. And the map on the right is, if we look at the long-term estimate of total nitrogen concentration relative to standards, so this is the Illinois River Basin, there's a range of standards, and it varies based on different regions, non-wadable and wadable streams. And just the color indicator just basically shows that the orange indicates almost a binary response that most of the rivers are above some standard. But if we look at this across 84 seasons, we can start to look at how things change over time and quantify new metrics like probabilities. And then we can also look more at what are the causes in individual source components. On the left is the total makeup. So if we just pick one concentration standard and look at the probability that the concentrations above that standard, that's what that shows. But then we can break it into its individual components. The new inputs, that would be like a fertilizer applied that season versus the lag mass. And you can see where the influence of all the point sources are. And it looks a little more pronounced when we look at phosphorus. The wastewater treatment in the Illinois River, it has an influence in terms of increasing the concentration in the main stem of the river all the way down close to the outlet. Okay, so that's one of the exciting parts that we're looking at. Is we can look at how things change over time. We can look at how things change in terms of extremes from one season to the next, and look at individual source components. And we see that when we want to try and identify source components and what is contributing to water quality at this location versus this location, extrapolating the monitor data by using other proxy data is really important. And so it better highlights things like, well, treated wastewater is a major source component, but we can better see where are the hot spots that it better kind of isolates that, because we can show relative to the lagged component, because there is a lag mass component that's traveling through soils and groundwaters. And since we're bringing in all these data sets, we can start to make inferences about how changes in hydrology and soil. So if you change vegetation, you change soil structure, it has effect on the delivery, and we can represent those processes in a lumped fashion, but we can still quantify them with this type of modeling framework. And so next steps, we're really excited to look more at the trends, look at marine discharge points, integration with other data sets. We gave many examples on this talk, that was based on really all the other presenters. I think we have a list of some other ideas. We mentioned lakes and reservoirs. And there's other approaches that we're considering, like integration with machine learning. And that's where a lot of this feeds into. We're not working on this in an isolated bubble. It's very much tied to other projects where we are trying to advance things like the representation of the digital stream network. So that's where a lot of Michael's work could come in, and we're continually trying to improve the representation of the monitored network. And so, all the work that Christopher and Colin's doing really helps with that. And I mentioned the machine learning, so there's a new project there, and we're hoping that our results feed directly into that and really lead to some exciting comparisons. Okay, I will stop there. Thank you.
Great, thanks so much, Noah. There was a note that came through the Q&A that chat's disabled, and that is true. Questions should come in through the Q&A, and we didn't get any. But if anyone wants to enter something now, feel free to do so. If not, we can kind of wind things down. One question I had for you, Noah, is just regarding the diversity of models, hydrological models out there. I've never quite understood exactly why there is such a diversity. You know, there's Sparrow, SWAT, there's a bunch of others, but are they all getting at different questions? Is there a need to harmonize these models?
Yeah, that's such a great question, Matt. In terms of harmonization, yeah, let's first take a step back and think about, I think you're right on that we apply different model approaches based on the fundamental question. Now, from my understanding, we would pick something like SWAT if we really needed to understand very detailed nitrogen processing within soils, within groundwaters of very particular basins. And that requires a lot of data sets. There's a lot of additional equations. So it just is more complex. But there's value to that, where we can run scenarios perhaps and identify very specific elements of a very specific basin. But when you want to ask a question like, well, what is the contribution of that small little basin 100 miles downstream, then you need more of a Sparrow type of approach. And so we've talked about things like, well, we could probably spin up a Sparrow model with fewer data, but those results might help constrain and almost be used as calibration data or even boundary condition data for a SWAT model. So that's where the integration ideas perhaps can be fruitful, where it's a downscaling approach. So like if you develop a very specific model in the basin and move it to another basin, you're like, oh, that basin doesn't have a key data set we thought we might need in this basin. It makes it really hard to develop a comprehensive perspective and accumulate all those predictions through. So then you kind of need Sparrow to check it a little bit, even though, Christopher pointed this out, like when you zoom into very specific reaches with the Sparrow model, because you're at such large scales, you're doing a lot of lumping in terms of understanding and representation. So there's a cost associated with that. And so you might not be able to say something very specific about it, but you need to be able to connect all the dots. So I think your question, Matt, is a very intriguing, active area of research, and we should keep that discussion going. And I would like to hear other ideas from people that are more versed with SWAT models, because I've heard talk that, hey, we are developing CONUS-wide or national scale SWAT models. And yeah, I haven't really followed up with exactly where we are with that. I think we're on a good path with the Sparrow stuff and the dynamics and keeping things comprehensive and trying to connect headwaters to estuaries. So I don't think that we're doing something that we're like advocating for, oh, this is the only way to model. We're saying, hey, this is a value to help other modeling activities, and we need to be creative in how to most efficiently connect those together, where the modeling we're doing can help SWAT modeling and vice versa. Does that answer kind of help?
It does indeed. Thanks for that explanation. Again, Noah, thanks for the presentation, and we'll go ahead and wrap up for today. I just wanted to thank everyone for participating, and also remind people to please register for the Phosphorus Forum by going to the Sustainable Phosphorus Alliance website at phosphorusalliance.org. I also want to thank the presenters for all the time they put putting these presentations together, especially to Michael Meyer for helping to organize all of this. So with that, we'll go ahead and close things out. Thanks again, and we'll see you next time.